Let's take a look at magnetic materials. We want to start by saying that atoms, molecules, liquids, and solids can actually display magnetism. The strong case of an interaction is something like a compass needle interacting with the Earth's magnetic field. We say strong because the dipole moment that is equivalent to this compass needle is very large, and it's because this material itself has a permanent magnetic moment which interacts with the Earth's magnetic field. The torque causes the needle to align. Well, we'll see some other kinds of magnetism. This is ferromagnetic material. We'll take a look at some much weaker magnetic systems and then come back to the ferromagnetic materials. The secret of all of these materials, so magnetic materials, are dipoles. We're talking magnetic dipoles. Can't explain any of the magnetic effects without getting to the concept of a dipole. And the simple definition of a magnetic dipole moment is that it's equal to a current times a area. And we'll take this as a vector and we'll take m as a vector. And that's associated with a current that's flowing around the area A, and the right-hand rule gives you both the direction of the vector A and the magnetic moment being proportional to this area vector. We can imagine then that if we have a system with little tiny circulating currents, we would have dipole moments associated with them. So in magnetic materials, the observed effects, which may be forces or torques, are due to the influence of the magnetic field on magnetic dipoles that are in the material. And I want to emphasize that these might be permanent dipole moments, say for atoms, or they may be induced dipole moments, again for atoms and molecules. So in other words, you apply a field, you induce a dipole, which then interacts with the applied field. Just to remind you, there's an analogy between dielectrics and magnetic materials. What it is that you have applied electric fields that are being applied to a material that has electric dipoles, and the behavior that is a result of this interaction is the material becomes polarized. Remember that if you have the dielectric between electrodes, a capacitor, this will lead to the increase in capacitance. We'll find out later that magnetic materials can enhance other properties, basically inductance of a material, because of the magnetization of the material. So where does this arise? Any object that's made up of atoms or molecules will have electrons that are moving. Classically, these are electrons moving in orbits around the nucleus. With each electron in an atom or molecule, we can associate a tiny magnetic dipole moment, which is due to A, the electron orbital motion, and we'll see that this is kind of tricky if we treat it classically, or electron spin. Spin is angular momentum associated with every electron, and that can lead to a magnetic moment associated with the electron. Some atoms and molecules have permanent dipole moments, or external fields, magnetic fields, can induce magnetic dipoles. And so we'll be talking about these two types of magnets associated with atoms or molecules. But before that, we want to define a magnetic field called H, and to do that we remember that B is the magnetic field that we've been using, and that's called magnetic induction formally, but we've been just calling it the magnetic field. If you recall, B is like the E field in the sense that E is dependent upon the free charge that is in the vicinity of a system and the bound charge. So if you have both bound charge and free charge, E is dependent on both of those. Well, similarly, B is dependent upon basically free currents and the magnetization vector, which is inside the material, and we'll define that in a minute. H is the magnetic intensity, which we call the H field. H is like the displacement vector. And what that means is that this depends on free charge only. H depends on free currents only. If we look at free space, B is proportional to H, where in free space this proportionality constant is mu0. And that's the same mu0 that we've been using before. So I give the magnitude, which is 4 pi times 10 to the minus 7, and the units are newtons per ampere squared. And remember, we called this the permeability of free space. So we can quickly get the units of H by just dividing the units of B, dividing that by the units of mu 0. That's what I've done here. And so the units of H are equal to amperes per meter. Let's talk about the magnetization. So this would be a quantity that is defined throughout the volume of a magnetic material. And so let's suppose we apply an external field. Let's just call this one B external. We end up with some dipoles aligning, so there could be a net alignment, and this could be just partial alignment in some cases, of these magnetic dipoles. Remember that these magnetic dipoles might be induced by the application of this field. So we have both cases. If they are simply a bunch of little dipoles that already exist, then this field is going to try to align them, and that leads to a magnetic material. We call that material magnetized if it has this situation where it has these magnetic dipoles at least partially aligned. The state of magnetic polarization is described by a vector capital M. That's called the magnetization of the material, and it's defined as the magnetic dipole moment per unit volume. If you look at the units of M in terms of a dipole moment per meter cubed, that will reduce to amperes per meter. So remember, the dipole would be current times area. That's the dipole moment. And then you divide by meters cubed, and you'll end up with amperes per meter for the unit. Now if you remember, this is the same unit as the surface current density. We call that K. And so that has the same unit, amperes per meter. And that's important because surface currents are going to be related to generating magnetization. To nail this analogy again, M is analogous to capital P, which was the electric dipole moment per unit volume. And we called that the polarization density, and that was what we got for electrostatics. And for capital M, it's the magnetic dipole moment per unit volume. So let's imagine we have this volume of material, and it's full of these little dipoles, M sub I. These are all vectors, and so they may be the same magnitude, but they're pointing in all kinds of different directions. They don't have to be the same magnitude. The net magnetic moment of this volume V is the sum over all the M sub i's. If we sum them up, we'll get a total dipole moment. If these are aligned, then M total will be larger than in the case where they're totally random, because then this sum would be small. So we have to realize then that as we increase the alignment of these dipoles, we're going to get a bigger dipole moment. Therefore, if you look at the magnetization, which is proportional to this total magnetic moment, it will be large in that case. Or if this is 0, this will be 0 again. Let's look at Ampere's law. We're going to consider a solid that might have a non-zero capital M. What we're interested in is how these quantities, the vector quantities BH and M, and the I enclosed are interrelated. So let's go back to the case where M equals 0. Remember, we had a path of B that was related to I enclosed with a integral of B around this curve C. And so here's the integral, so we can say this is around the closed loop C, and it's B dot dl integrated along that path. If we have no magnetic material, or if M equals 0, then this is equal to mu 0 I enclosed. That's Ampere's law that we've used in the past. However, if we have a magnetic material where M is not equal to 0, then we're going to have to put that into this equation because B depends on M. The way we do it is we just simply add this integral that we have here. And so we have m0I mu 0 times this integral here. Let's take that. This would be the revised Ampere's law for a material non-zero capital M. So let's solve for I enclosed, and so we just bring these integrals together and combine the integrands like we show here. We now come back and introduce H. H depends only on the free currents, and the only free current in this vicinity is I enclosed. Just to remind you then, I is the motion of charge in this vicinity here. The corresponding I enclosed within the curve C is what we're talking about. The integral of H dot dl is equal to I enclosed because that's the free current, and so this would be Ampere's law for H. If we look at these two integrals that are equal to I enclosed, we can set them equal to each other here. The question is, what happens if we change the curve C? So we change to a different curve C. It's a loop and it has some I enclosed. Then what we see is these two integrals stay equal to each other. They may change values, but they stay equal to each other. This holds for all paths that are closed, and so we can equate the integrands. So doing that, then we have basically B is equal to mu 0 H plus mu 0 M. So all we've done is taken this integrand equals H and solved for B. Notice that if we go outside the material, capital M equals 0, because capital M requires that we have dipole moments. If there's no material there, there are no dipole moments. That gives us our old friend B equaling mu 0 H for free space. Repeating that then, in free space we have B equals mu 0 H, and if we have non-zero capital M, if we're inside the material, then we have this relationship here. Sometimes we call this last term B magnetization, and sometimes we call this B0 because that's the contribution to B just due to the free currents in the vicinity. We're going to jump into a type of material where M is linear, and what we mean is M is proportional to H. So if we go back to what M would look like, it would be a constant times H because of the proportionality. Chi sub M is the magnetic susceptibility. So you can see there's some analogies with dielectrics. This is a dimensionless quantity. It's material dependent, and it's positive for paramagnetic materials, and it's minus for diamagnetic, and we'll do a better job of defining these later. The values are typically 10 to the minus 5 in magnitude for the diamagnetic materials. For para, it might be as large as 10 to the minus 3. So they're small. If you go back to our B equation, you'll notice we have an M here, but we have this linear equation for M, so we can stick that in. Doing that, here's our mu 0 factored out. Here's our M right here. If we factor out now capital H, we'll have mu 0 times 1 plus chi sub M times H. We're going to redefine the constant between H and B now. With the magnetic material, we'll have this value mu. Mu is equal to, as you can see, mu 0, 1 plus chi sub M. Okay, so look at it again. This is B. This is the constant in front of H. But we've already defined this mu as being the constant in front of H, and so therefore we can set those equal. What is mu? Well, we had mu 0 being the permeability of free space. Mu, without the 0, is the permeability of material. Well, it's pretty simple to see that if we define a relative mu as just the ratio of mu over mu 0, that will be equal to 1 plus chi sub M. And so we have a relative permeability, which again is dimensionless. And I think you can see the analogy between mu and epsilon r that we use for electrostatics. This page here is unreadable, and basically what it gives you are the units for a lot of the quantities that we've defined. Some of these you don't have to worry about because we're not going to use them. But for example, we said H was amperes per meter, here's M with the same units, so on. You can find these at this website. Take a look at the ones that are popping up in this lecture. Here's the linear equation for M, so these are linear materials. We call this the magnetic susceptibility of the material. We've said the units are dimensionless. Let's take a look at the types of magnetic materials and chi sub m. We've already said the diamagnetic materials have a magnitude of about 10 to the minus 5. This is minus, as we will see, because the magnetization is in the opposite direction to the applied field. The superconductor systems have a chi of minus 1. This is the largest that chi sub m can be. What you see here is that you have a material which is a perfect diamagnetic material, and that has to do with the fact the field is totally excluded from the material itself. To bring that home, if you come back to here, if you let chi sub m be minus 1, then the B inside the material will be 0, because this quantity here will be 0. So it excludes the B field from the solid. The paramagnetic material, which we will also talk about, has a slightly larger value of chi sub m and is positive. The magnetization that results from applying a H to a paramagnetic material aligns the dipoles in the same direction as the applied field. So that's why this is plus. Ferromagnetic materials have plus chi's, and they're huge. This says 10 to the 3 times 2 10 to the 5th. Let's review then the origin of magnetic moments in solids. First can be the orbital magnetic moment of the electrons. This can lead to an induced dipole moment and or non-zero values at all h. The electron spin can be another source of magnetic moments. Those can interact with external fields also to give you magnetization. We just mentioned the spin magnetic moment of the nucleus. This is very small compared to these other magnetic moments. We usually neglect those. You don't want to neglect them if you're going to get an MRI, because magnetic resonance involves coupling magnetic fields to the magnetic moment of the nucleus, and only works because the nucleus has such a magnetic moment. If we take atoms and electrons and look at the associated magnetic moments, if we just treat it classically, you can imagine that you have this electron orbiting the nucleus. This big fat guy should be shrunk to a point. And the motion that you see here would result in some angular momentum associated with that electron. In a hand-waving way, if a system has angular momentum that's charged, you could end up with some magnetic moment. If the electron's going this way, the magnetic moment associated with that current would be in this direction here because of the negative charge. A similar argument would be for the electron. If the electron has some angular momentum s just due to its existence, then there's a magnetic moment associated with that angular momentum, and it's in the opposite direction as I've shown here. So these two moments in an atom could add to give us the total atomic magnetic moment. So here's the orbital moment and the spin moment, like that. Let's take the case where we just have the nucleus and the electron orbiting without, we won't worry about spin. We can say then that there's this electron motion generates a current, and the magnitude of that current is the charge per unit time to go around the circle once. If we take the period then in terms of the velocity of the electron would be related then to the current by taking E times V over the distance, which is 2 pi r. Just to nail this, capital T is equal to the distance divided by V. So if you take 1 over T, you get this. The direction of the current is in a direction opposite to that of the electron. That's because of the negative charge here. The dipole moment of this current would be I times A, and the area is just pi r squared. We've already derived I, so putting those together, we end up with this equation for the orbital magnetic moment. If we take into account the fact that this is negative, and we take the z-axis along this direction here, then this is going to give us a negative orbital moment, and that will be minus in the z direction EVR over 2. And I forgot to change this. This should be reversed. The m orbital should be in the negative direction. If we can find V by using Coulomb's law, this would be treating a single electron orbiting around a nucleus. We can assume then that the initial condition is that we have zero magnetic field. So B or H is zero, which for a linear system, if this is zero, and vice versa. This is the resulting equation here. This would be if B equals 0. So we have the Coulomb force is equaling the centripetal force. Just to be careful, m sub e is the mass of the electron and not a magnetic moment. Now we're going to turn on B, and this is the picture of it. Here's our magnetic moment in this direction here. V is going around this way. The real current is going this way, and the B field is along the plus Z direction. If we have this B, we are going to add this quantity here in terms of the force, which will be a force that contributes to the attractive force. If we add to the attractive force of the charge, the nucleus, pulling on the electron, this quantity here, we will get the centripetal force. But we're going to assume that the velocity changes. So the V goes to V prime when we applied the B field. If we put this term in, then we'll have a situation where we've applied B and we're assuming that that does not change the radius of the orbit. And there are some quantum mechanical arguments that would be associated with that assumption. So look what we have here. We have two equations. One has a V in it, one has a B prime, and we're going to associate V prime and V with a change in velocity, delta V. So we combine these two equations. So here we have the equation 2 and equation 1, which were, let me go back, are both equal to the Coulomb force. So all we've done is solve this for the Coulomb force. We already have it here, and we set those equal to each other. And that gives us this equation here. This contains both a V and V prime. Rearranging this then, so solving for V prime B, we have the difference between the squares of V prime and V times this quantity here. We can expand that to V prime plus V times V prime minus V. We're going to assume that this change is small. In that case, we're going to be able to say that the positive addition is going to be 2V. We're going to let the negative difference be delta V. If we put that in, then here's our EVB prime, EV prime B, which is approximately equal to 2m sub ev over r. We've taken this quantity here and set it equal to 2v. Now we have an equation for this change in speed that is then related to the fundamental constants and B. If B is greater than 0, then delta V will actually increase in velocity. So the electron will have an increase in speed. And so delta V will be positive because everything else is positive. We can say then what happens to the orbital magnetic moment? Well, remember that that was related to this quantity here. So if V increases, then the orbital moment, due to the electron orbiting around the nucleus, will increase in the opposite direction to B. This minus sign is saying that the B field in the region of this system is going to decrease. And so that means that this minus sign is really at the heart or root of diamagnetic behavior. If the electron would have been orbiting in the other way, it would have been slowed down by the magnetic field. However, if you look at the change in the dipole moment, it is again opposite to the direction of B. What we're talking about then is if we have paired electrons, where one is going this way and the other is going this way, they both are going to contribute a reduction in the B field due to this magnetization. So in the presence of an external magnetic field, the dipole moment of each orbital will be slightly modified, and all these changes are anti-parallel to the external field. So using our classical approach, if we solve for delta V equaling this, we can then write that the change in the magnetic moment is equal to this quantity here. And so if we put in our delta V, then that will be equal to all of these constants with the B field here in the minus direction, minus Z hat. So I've collected all those, and this is the equation for delta M in terms of E squared R squared 2 over M sub B Z hat. If we wanted to, we could put in H. I'm not going to do it, but this would be then changing B into H, and so we'd introduce a mu 0. Before applying B, in the 2-electron case, all the orbital M's were 0. So we didn't have it, by the way, any orbital angular momentum. Delta M in the z direction is the induced dipole per atom, and each and every atom contributes a delta M in the same direction. Okay, this is very important. The induced dipole for every atom is in the same direction, and that is in the z direction, which is in the same direction as the B field. So if you had a density n of atoms, so n atoms per unit volume, then capital M is equal to little n times delta M. So this is the total magnetization due to this collection of atoms which have a density little n, and this is the change per atom. So putting that in, then we have the net result for B field or an H field, whichever one you like, where very simple constants and the density of the material gives you a magnetization which, if B is 0 or H equals 0, disappears. So it's totally dependent upon the presence of a field. So these dipole moments are all induced by the B or H fields. So if you set the field equal to 0, you don't get any magnetization. This is diamagnetic behavior. If we relate M to H, as we did before, if we have a diamagnetic material, this quantity here is negative and small. So it's first of all, it should be less than 0 and does not differ too much from minus 10 to the minus 5. So here's our B or H. Here's our induced magnetization in the opposite direction. It's present in all materials. It's usually too small, and in particularly it's very difficult to see if you have paramagnetic behavior at the same time. It's much weaker than paramagnetic response, and so therefore you really can only observe it in materials where there is no paramagnetic behavior. So there's several materials that will do this, and just a simple example is water. Water is diamagnetic. So what happens if you look at the magnetization versus H? Well, as we expect, it's linear, it has a negative slope, and it goes to 0 at H or B equal to 0. And so we have this relationship that gives us the magnetization in the opposite direction, and as we said before, it exists in all materials. It's observable only when the electron spins are paired to get rid of the paramagnetic behavior. High temperature will also get rid of the para, so you could get rid of that by just heating the material, and you will be left with dia, because dia does not depend on the temperature, and that's what this says. Diamagnetic chi sub m is temperature independent. Diamagnetic chi and M production is reversible. So if you start on this point here, you form diamagnetic material, lower the field, it goes right back to 0. Some examples of minerals which are diamagnetic are shown here, and these are the values of chi sub m. And realize that, for example, 10 times 10 to the minus 6 would be 10 to the minus 5. And so if you look at the values of chi, they differ primarily because minerals are dirty, and so you'd have different mixes of materials here. But you have quartz, calcite, graphite, sodium chloride, and zinc sulfide, all having the diamagnetic behavior. There's a lot more materials that are diamagnetic. So next time we'll go to other kinds of magnetic materials, those that are paramagnetic and those that are ferromagnetic.